Okay, so the recording started. So hello everyone, welcome to today's Origin seminar. Our speaker for today is Dániel Apai. Dániel is a joint professor in the Steward Observatory and Lunar and Planetary Laboratory of the University of Arizona. So he's the PI of several large research projects, including the Nexus for Exoplanet System Science that support this seminar. He's also the PI of the Alien Earth project that he is going to introduce today. So okay, Dániel, the floor is yours.
Thank you very much, Xianliang and Serena and Sebastian for organizing the meeting and for all of you for joining. So as mentioned, today I wanted to give a bit of an introduction to Alien Earth, what Alien Earth is, and how it connects to the search for habitable worlds around nearby stars, and show a couple of exciting examples for science results that are emerging from Alien Earth. And this is one of the about 4 or 5 Origin seminars that we will be this semester will be using to for the Alien Earth team to highlight and showcase some of the results, and then interact within the team and also with the broader community to connect. So I hope that from this talk you will have a good sense of what Alien Earth aims to do and the many ways you can connect to our team if you are not already working with us. So I think there are really many ways that our community can pull together. The Nexus ICAR, interdisciplinary consortium for astrobiology research, of which Alien Earth is part of through the Nexus Research Coordination Network, is really providing a good opportunity for all of us to work together. The science results that I'm going to highlight today, just a few from the many projects and results that are emerging from Alien Earth. These are done in collaboration with Jeremy Dietrich, Alex Bixel, Ritwik Basant, and Renu Malhotra. Jeremy is a graduate student, Alex is graduated recently, Ritwik is an undergraduate student, and Renu is, of course, a professor at the Lunar and Planetary Laboratory. So let me start with this slide. So for many years, we have heard about the Astro 2020 decadal survey and what will or will not, or what may reveal and recommend. And now we know that it's came out, and I think it provides a major milestone for the field. So I want to speak a little bit about life beyond the solar system, the search for it, and then also life after the Astro 2020. What came out, what are the recommendations, how we go from where we are to where we want to go. So Astro 2020, it's of course a massive document, an excellent document with a really good quality recommendations and assessment of the field. 700 pages or so, so I'm not going to even try to summarize it, but I want to highlight a few points that are perhaps most important for exoplanet search for life. And so these are, I would say that it's very exciting for someone, myself working on exoplanets, to see how highly the Astro 2020 decadal survey ranked exoplanet science, and specifically habitable exoplanets and atmospheric biosignatures. It is a major step for the field, and also reflects the amazing progress that's being made. It recommended very highly the US Extremely Large Telescope program. So this is the GMT and the TMT, and I'm very excited about the science that will emerge from those programs. In addition to the pushing forward these ground-based facilities, the recommendation is always also, and I will mention it primarily here, for a 6-meter class mirror diameter mission for a cost that may be around $11 billion or so, and precursor technology maturation. The goal of this mission the primary goal is to search for habitable zone exoplanets and characterize them, search for signatures of life. It has also a variety of other astrophysical, of course, utility and very exciting science that can be done with it. And I want to take a lot of the motivation for this talk from this kind of recommendation. So I think one of the things that is interesting to point out is that this mission, as proposed here, will study about 25 habitable zone planets, assuming an ETA-Earth value. And that will mean that basically with the cost just nominally, each of these planets will cost about $400 to $2 billion. And so if the ETA-Earth value is lower, then actually the individual planets and the money we spend on them will be even lower, or more money. So it is actually very important that we understand which are the right targets, which are the right measurements, and we do that before the mission is defined fully and targets are selected. And I think here a key challenge is that planets are complicated, especially if we speak about a planet that is cold, Earth-like, has a variety of atmospheric and climate processes, and potentially also an alien ecosystem. So we must not underappreciate the complexity. And I think much research is needed to establish, basically enable a framework that will allow us to select the right targets, make the right measurements, and then draw the right inferences. So the LUVOIR and HABEX teams have done an excellent job in really setting the stage for this. This is just a figure from the LUVOIR final report that shows kind of a triangular approach, how you start from basically using precursor information to establish a target list, and then photometry and proper motion to narrow them down, constrain the orbits of potential habitable planets, search for atmospheric water. Once you find atmospheric water, then you narrow down further your candidate list and carry out more and more observations, drilling deep to understand finally their potential for habitability and really their potential for life. So this is a process that is difficult, obviously, and much of Alien Earth's work, and what I'm going to tell you about, is aiming to provide the contextual information, the guidance that we need to actually execute these steps successfully. So some of the questions that I take away from a diagram like that, and you could make your own list, of course, are the following. How common are habitable worlds? Eta Earth value, it's very important in driving the mission designs and the capabilities that we require. What is the diversity of Earth-sized planets? When is a planet truly Earth-like? And through which pathways can truly Earth-like planets form? In other words, if there are different pathways, what fraction of them, for example, end up with inhabitable planets? We also know that planets don't exist as individual objects in isolation, but rather they are members of planetary systems. Those planetary systems can both impact the formation and evolution of these planets, the other members in the planetary system, and also provide information for us to figure out what the properties of the planet may be. So it is, I think, very important that we recognize also planetary architectures as a field of study beyond individual planets. So one operational question is how many targets, exo candidates, we actually need to achieve our science goals, and what are really those science goals exactly? And what is the diagnostic power of an exoplanet survey and space mission architecture as a function of the targets we select, the kind of data that we collect, the kind of ancillary data that we have at our disposal when we are interpreting the data? These are really important questions, I think, that will probably have major impact on the telescopes and mission designs that we end up with really building. And so why this distinction? I think most of you probably know, but I think it's a really illustrative example that Earth-sized, being an Earth-sized planet close to or within the habitable zone doesn't necessarily mean it's Earth-like. And so one example, of course, is Venus in the solar system, which is very similar in size to Earth. It's very similar, very close to the habitable zone. Probably they started also very similarly in terms of their initial conditions, yet they are very different in terms of their potential for hosting liquid water on their surface or providing a habitat for an ecosystem as we know it. So it is important not just to focus on where the planets are and how large they are, but to really get the contextual information and understanding them. And so this is, and it is not just directly observable sources that we have to think about, or sources of information. In 2018, I led a white paper that many of you co-signed too, pointing out that when we are to determine whether or not a planet is habitable, some of the key properties will be observable. So we may be able to directly or infer the mass or through observations determine the radius. We will be able to establish the present day irradiation levels, rotation periods, etc., atmospheric composition, but there will be critical parameters and pieces of information that remain beyond what is directly observable and measurable. So a couple of examples for this is really the detailed bulk composition. We do need to have a sense of that if we are to assess, for example, climate cycles on a planet and climate stability. The organics volatile inventory, orbital evolution, whether or not it has a geological activity that is comparable to Earth, and what was its evolutionary history, both in terms of atmospheric evolution and volatile losses. While we don't need complete understanding, we need some level of understanding of these processes and parameters for us to be able to really assess credibly whether or not a planet is habitable and can really be to provide a context for interpreting an atmospheric biosignature. So other teams have also made similar suggestions and recommendations. And I think within Nexus, which really stands for Nexus for Exoplanet System Science, the idea is exactly this, to basically look at planets in a general context and understand them as system of systems. So alien Earth comes into this picture basically as an indirect continuation of our previous project, Earth in Other Solar Systems, in which many of you have been participating. It was funded for 5 years, actually 6 years with extension, by NASA. We were the first among the first members of Nexus, and this was an extremely exciting opportunity to work with a large team, with many of you, to answer big questions that we could not do in a smaller team. So this is just a couple of random high-level results that I particularly liked for their programmatic importance or impact. But EOS has led to over 155 papers, maybe 160 by now, about 5,000 citations, and that keeps on growing. It made real differences, I think, in the community, with some of these papers receiving hundreds of citations. Alien Earth builds on this and basically takes it to the next level. EOS's question was, how do you form habitable zone Earth-sized planets, and what are the processes that can influence their habitability? Alien Earth is taking the lessons learned and the methods developed and the results and the community developed for EOS, expands on that and takes it to a direction where we are aiming to answer which nearby planetary systems are likely to host habitable planets and life. So this is basically taking plant formation aspects, exoplanet demographics, specific observables of individual planetary systems and planets around in the stellar vicinity. Why are nearby planetary systems emphasized? I will touch on these, but nearby planetary systems are the ones that we will be able to assess and study in the greatest level of details over the next decade. These are the ones where we will probably be able to search for signatures of life. Most of the planets found by the Kepler system, a kiloparsec or two away, remain beyond our reach. So we need to focus on nearby planetary systems that are close. So Alien Earth is an amazing team of scientists. We have over 40 people, 30 plus faculty and researchers from not just the US, but across the world. Many excellent students have already joined us or will be joining over the 5-year duration of the project. It's a $6 million project, so we'll have opportunities to work on a broad range of topics that are all connected. So this is just a high-level assessment of what is included. I don't want to go into too much programmatic details here, but we have 4 modules. The first module explores conditions and timeline for planet formation. The second module explores the impact of planet formation pathways on the planet's composition. The third module explores habitability and threats. And the fourth one takes this information and then contrasts it with the capabilities of potential future missions to guide them and then to provide a context to interpret results from those missions. So there's just, as with EOS, we do expect between 150 and 200 refereed papers, so it's going to have a massive and exciting impact on the field. I will only highlight a couple of directions that we are going to, some of the ones I'm most directly involved in or leading. I will mention that we very much see Alien Earth not just a project for our own team, but it is basically foreseen as a hub to interact with the broader community, and several people have joined us already, and I'm sure others will. We are really open for ideas and looking forward to opportunities to collaborate with more of you. So I wanted to focus this talk a little bit on specific results also and highlight the research that's going on. And one important aspect that I already mentioned here is the search for nearby planets. And I mentioned already that these nearby worlds are the ones that are going to be strategically the most important. And while Kepler was, for example, intrinsically a statistical mission in nature, we now are transitioning to, of course, the next era in exoplanet exploration, where we want to understand individual systems better, individual atmospheres better, individual planetary systems better. And you may think that with all the thousands of exoplanets known today, the nearest ones have all been found. So we know that within just 50 light years, which is 15 parsecs or so, a very small volume, speaking in terms of, from a galactical perspective, has around 1,560 stars. And we would expect, just ballpark, that there could be probably around 10,000 exoplanets with, of course, significant uncertainty there, but that's the order of magnitude we should probably expect. And maybe there could be habitable zone Earth-sized planets, maybe around 500. Some would put this number higher. I'm probably more on the pessimistic side. But it is a pretty significant number of worlds, even within just 15 parsecs. But how much of this we know? Actually, we know only about 166 or so exoplanets out of the 10,000 that may exist. And in terms of the habitable zone Earth-sized planets, the number is roughly 5, depending on exactly how you define habitable zone and how you exactly define Earth size. But the point is that we really are missing the vast majority of these worlds, even in this closest, smallest volume to us. So one of the projects within Alien Earth is Project Eden, that is following up nearby planetary systems and especially late M dwarfs, combining our data with TESS observations where possible, and we are searching for and following up small transiting planets in this small volume because of their strategic importance. And we will give another talk on Eden, but today I will focus on a couple of other projects that link together well for this presentation. And in particular, because of their importance to providing an example and a framework for integrating knowledge across the Alien Earth project. So, and the component I need to bring in here is the emerging patterns in exoplanet population. And so we have heard many talks about these exciting results that emerge from exoplanet populations that we now can study, mostly, but not exclusively, due to the Kepler mission provided sample of exoplanets. So we now recognize multiple teams typically find and confirm these results. And I highlight here some of the work also from EOS that, especially where it was leading these discoveries. We now recognize that short period planets are very common. The solar system is an unusual planetary system with its basically interior being unpopulated. The most common periods for planets are around 7 to 12 days, and there's a broken power law that describes quite well planet distribution. We know that planetary orbital spacings share a similarity. It turns out that multi-planet systems often have similar architectures. The orbital period spacing is similar in log space. Other ways it was expressed too is that orbital period ratios are clustered. These are two examples for this. Many planetary systems are also dynamically packed. So that means that it's very difficult to add additional planets to them without making them unstable. And this is a really exciting, I think, finding. And there were multiple teams that have published this and similar results. Planetary orbits are often aligned also. So inclination distributions for the planets were found that they are well mapped with the Rayleigh distribution. It is not true for every single system, but it is generally true that most of the planetary systems tend to be quite flat. A really nice example of both of these that I mentioned is the TRAPPIST-1 system, which is a really very well-packed planetary system, which is also very flat. There is also the recognition of what people call a piece in a pod, that planet sizes in a given system tend to be correlated. They are not randomly distributed. You tend to find similar planets in a given system in terms of their sizes. So many talks have been given on these results, of course, and I'm not going to go into great depth here, but what I want to show is how we can use these kind of correlations to advance our understanding of nearby planetary systems. Then let me go back in time and just start with one project that shows this as an example, and then evolve further. It's been now about 6-7 years that I've been thinking on how to combine statistical information from exoplanet demographics with specific information on a given system to better our understanding of the system properties. So let's go back to Proxima Centauri b. And so this was a study that we published very shortly after the discovery of this exciting world, Proxima Centauri b, from a radio velocity survey led by Anglada Escudé et al., which after many years of monitoring, we were able to ascertain the existence of a planet with an 11.2-day period around Proxima Centauri, the closest star and the red dwarf, of course. And they derived from the amplitude a minimum mass for the planet of 1.3 Earth masses. And this is a very exciting planet and has sparked many follow-up studies. Most of them are theoretical studies, and most of them assume that this is a habitable zone, 1.3 Earth-sized mass planet. We started the project right after this discovery with Alex Bixel, who then was a graduate student at Stewart, to explore what is the nature of Proxima b. And so the fact is that the RV measurement, of course, doesn't actually give you the mass. It gives you a lower limit on the mass because we don't know what is the inclination of the system. So how correct are we to assume that it is 1.3 Earth masses, and what else could we say about the system? So this was a pretty simple precursor study. What we basically knew is that while we have very little information still about Proxima Centauri, we know quite a bit about M-dwarf planets and their occurrence rate. So we were able to take basically the occurrence rate of M-dwarf planets as a function of their sizes and use two different mass radius relationships that were kind of bracketing options out there to derive what would be a prior mass distribution for a planet. So if we found an M-dwarf planet, what would be basically just on how common small versus large planets are, that would be the prior mass distribution. And then, of course, we have a measurement that constrains this, and which gives us a lower limit of 1.3 Earth masses with an uncertainty that is not negligible. And so we can actually use Bayesian approach to figure out what is the posterior mass distribution for Proxima Centauri b. And so what you see here on the lower right is the result of this study. There are really two components here. This purplish color is when we have a more likely rocky composition, and the pinkish color is when it's more likely to be a Neptune like planet, a mini Neptune. The result of this analysis is that, in fact, you see that the 1.3 Earth mass itself is actually relatively unlikely. Almost certainly, this planet is quite a bit more massive than 1.3 Earth masses, and there is a long tail, of course, in the probability distribution that extends to higher masses. And there is still a non-negligible chance that this is a mini Neptune instead of a super Earth. So while this study is, of course, quite simple, I think it did point out, and it was an example where we had specific, uncertain and incomplete information, but specific information about one system, and we were able to put it in a context of exoplanet demographics and say, statistically speaking, more about that individual system and make predictions. So we took that, and I will show a couple of other studies from what Alex led, but let me show you studies that we are now leading with Jeremy Dietrich, where we take this idea and to a next level. And this is, I titled it Hidden Worlds Around Nearby Stars. So here in these studies, what we are trying to explore is where are the yet undetected planets. So even though Kepler ended with nearly 4,000 exoplanet discoveries, and maybe its most important result was really the exoplanet demographics, and TESS has found probably around 4,500 planet candidates as of now, and Radioverse surveys over 800 plus exoplanets. So we have pretty good handle on exoplanet demographics for short period planets. But in almost every single system where we detected planets, the majority of the planets remain undetected. There are very few exceptions to this statement. So the challenge remains that I showed you how much we are missing still from the nearby exoplanet population, but even in systems where we found 1 or 2 or 3 planets, many more probably remain undetected. So the question is now, can we predict in which orbits are yet undetected planets and what are their likely sizes and nature based on what we know about systems? If we can do that, then we have an ability, of course, to guide observations, to verify those predictions, characterize those planets, discover them, and then also in the future, you can use this kind of predictive tool if you are able to do this from, say, cursory information on a direct image system to figure out what the planets are and their properties. So, when I give this talk, this is the part where people often have the most questions. So I came up with a simple analogy that it's pretty simplistic, forgive me, but maybe it helps to highlight how this works. So of course, on this image, you see a cat, and there are many parts of the cat that are covered. But let me ask this question, and no need to really answer, it's just a rhetorical question. How many legs do you think is most likely the cat to have? How many eyes and how many heads? And can you predict based on this image where it is most likely that the cat's legs are? So I'm sure that most of you, while we don't know exactly the cat's properties, most of you guessed correctly in terms of the numbers of legs and heads and their locations and sizes. And it is straightforward for us to do, not because the original image gave us enough information. The original image was actually, if you don't know anything about cats, you could imagine many different locations and many different sizes of legs to be. But because we know that the legs tend to be similar, we know where they are placed, we know what is the average number of legs, for example, on a cat, it makes it quite actually easy for us to guess, in most cases correctly, what are the properties of the cat. So this is basically what we are trying to do for exoplanetary systems, and it turns out to be working extremely well for the inner planetary systems. So this is actually important. I think this is not going to be just, one of the many ways we look at exoplanetary systems. I think this is the future for the following reason. We will always have incomplete and often uncertain measurements of any given planetary system and its properties. Even with the fanciest telescopes we can imagine today, we will not have very good handles on planet sizes. For example, direct imaging planetary orbits will only be constrained to a certain extent. Some planets will remain unrecognized, etc. So we will always have to work with incomplete and often uncertain information. In the past, when we were limited to a single source of information, just transits, this was less, or just radio velocity, this was less obvious. But when we are integrating knowledge, we have to work with this kind of information. So that is, of course, a problem. We just don't have the high quality information that we would like on every planetary system. What we can do is to integrate population level trends here, which are much more robust, but of course they are statistical in nature. It means we cannot always make a correct prediction for every single planetary system, but we can make very correct predictions for the majority of the systems that are typical. So to do this, we developed the Monte Carlo simulation framework, and we can make predictions that are in the form of probability distributions for planetary orbits, planetary sizes, nature of planets, and potentially the number of planets. So this work is led by Jeremy Dietrich. He has done really amazing work in following up on this idea and developing it into a series of exciting papers. So the tool, the framework that we developed for this is the dynamical multi-planet injection tester, which obviously is Dynamite. We use the specific demographics information that I mentioned before, including planet radius and orbital period distributions, inclination distribution, relative size distribution, to create populations of test planets. Then we can test for dynamical stability and then further analyze. So this has now been, there are at least 4 or 5 referred papers that are using Dynamite. Others are submitted, and other groups are, more and more groups are using. Let me just show you basically an overview of what are the key components. So we basically generate, use input data for a specific system. So this could be a single system that we study, or in some cases, for example, the entirety of test planetary systems with multi-planets. We can use statistical models to create orbital period distributions, planet radius distributions, orbital inclination distribution, and orbital eccentricity distributions. These are sources of these distributions. Oftentimes in the literature, there are different descriptions of a given distribution, but oftentimes we find, of course, that these different descriptions, they actually describe the same underlying distributions, and they are typically not statistically distinguishable. So we can then use dynamical stability analysis to figure out which of those planets that could be drawn from these simulations are actually dynamically stable and could exist there. And then we can create basically a Monte Carlo based output for probability distributions. For dynamical stability analysis, we have tried and compared 3 different approaches: a mutual Hill radius based approach, which is basically gives you instant results, but it is also lacks a little bit of granularity in some cases, for example, for orbital resonances and fine structure. We have also used SPOC, which is a powerful machine learning based method developed by Dániel, which is based on short embody integrations, deep learning based on that training set, and then it's very efficiently in a couple of minutes can with high likelihood, but not with certainty, predict orbital stability, whether it's stable or not. And then also building on work by Walk and Malhotra, we can also use spectral fraction analysis that based on medium length embody integrations, and this is probably the most accurate and reliable, but it also takes more time. So this has been a really exciting journey, I think, on the papers I'm going to show you. This method, which originally we were really unsure whether we have enough information to make that and make these predictions, will they work? It turns out to be very productive and efficient. So in these papers led by Jeremy, and then another paper led by Ritwik Basant that I'm going to show you, we have carried out, in addition to predictions and analysis, a battery of tests. Oftentimes the tests we are doing is that we actually remove known planets from a planetary system. For example, look at the left-hand side. This is Kepler 154, where there was a planet, and we removed that planet, and we fed basically incomplete information to the system. Let me explain to see what the predictions are. Let me explain what is shown here. On the x-axis, you see the log period, orbital period of planets. The green planets are known planets in the system, minus the one that we removed. And then on the y-axis, you see the prediction where or analysis predicts the likelihood of an additional planet in the system. So here, basically, the question I stress is that we ask the system if there's an additional planet, where it would be most likely. And so, in fact, we do get back a very significant peak here at 9.2 days or so, which coincides with the planet that is a known planet that we hit from the system. So it was a very good prediction. And for the same system, it's not only, for example, the period is predicted, but you can see here the comparison of in blue, the predictions for the planet size and inclination and the actual measured value. So within very good constraints, basically a degree or so, we predicted correctly within the uncertainties, the planet inclination and also the size within uncertainties. And so this actually worked on multiple systems. We tried 1, 2, 3 different combinations of planets. This Kepler 20 is another system where we hit this planet and the highest probability there was identified, basically was corresponding to that planet. And in both cases, if there's an additional external planet, we have a prediction for where they will be. That was exciting. In a paper that is currently submitted and under review, this was led by Ritwik. This was by Jeremy Dietrich too. We have also tried this inner solar system. So we removed Venus. In this case, you see Venus covered, and Mercury, Earth, Mars, and Jupiter were input in the system, and we got the highest peak very close to Venus's orbit. If we did the same, but we removed Earth, we were able to predict that there should be a planet in the inner edge of the habitable zone, very close to Earth's orbit. These two colors stand for two different kind of dynamical stability assessment that Jeremy compared, and they both have the same prediction. In both cases, also basically we found whether we covered Earth or Venus, hid it from the algorithm, that the predicted size peaks at basically the right location. So that was also very exciting. So it works well for the inner solar system. It works for multi-planet systems. We keep on, with each paper, we keep on adding new functionalities to Dynamite. One newest, this is the paper that is in submission and under currently revision. Ritwik Basant, an undergraduate student, astronomy undergraduate student, has done an amazing job in adding a new component, leaky greenhouse and albedo, so that since we know the location of the planet, we would like also to provide a first guess for its potential surface temperature, under the assumption that this is a relatively thin atmosphere. So Mars or Earth-like, think about that, but not Venus-like atmosphere, not very thick. Or predictions are actually quite reliable. For the solar system, we can get back basically orbital periods, in this case for Mars, within 2%, and also the temperature basically within the temperature range that it's measured on Mars. So this is, while again these are predictive predictions in statistical sense, they work very well, of course, in the inner solar system and beyond. So we have applied in the original paper with Jeremy, we have applied this dynamical analysis framework for basically a variety of test discovered planetary systems. This list has grown since then, but what you see here were about 42 or 43 test multi-planet systems. The red dots stand for basically the planets that are known, and our blue shading stands for where is if there are additional planets in the system, what would be their most likely orbital period. So this is can make very specific predictions again for the periods and sizes of these planets. And in fact, in several of these systems, since we published this paper, planets were discovered at the locations we predicted. So that's quite exciting. Let me show you one specific example, applying it to nearby planetary systems. And it's kind of fun because these systems, unlike some of the Kepler systems at the kiloparsec away, these systems, for example, TaoSatis that I'm going to show you, have been part of popular culture, right? And humanity is thinking about worlds beyond for over a century. So TaoSatis is linked to many different, it's featured in many different science fiction movies and books. I learned that Captain Picard frequents an exotic bar in the TaoSatis system. All of these studies, of course, assume that there are planets in the TaoSatis system that could be habitable. Right now, we don't know that, and we set out and we published a study that I thought was very cool about the TaoSatis system with Jeremy. So this basically TaoSatis again, it's exciting. Because it is the closest single sun-like star to the sun at 12 light years. It's a little bit less massive than the sun, but it's otherwise quite similar. And TaoSatis itself was, of course, targeted in a variety of studies. Somehow, just a moment. Let me restart this sharing. It's okay. I will just skip this slide. So and can you still see my slides?
Yes.
Okay, thank you. Yeah, somehow the animation didn't come across, but basically for the TaoSatis system, the exciting aspect of it was that it was targeted by 2 radio velocity studies. And these radio velocity studies identified 4 planets. These are in green, marked here as in green, that these 2 studies concluded are reliable planet signals. And then there were 3 additional planet signals, so a total of 7 in the interior, where signals were detected, but it was not to the significance level that they would have considered a confirmed planet. Further out, there is also Debris that was rezoned by ARMA, and then there's a potential Jovian planet. So this is basically the system that we identified for a study, and Jeremy's analysis led to basically peaks. As you see, we only put in the confirmed planets, not the yellow, orangish diamonds. And what you see is that we predict actually 3 planets to be at the locations that turn out to be coinciding pretty close with the 3 planet candidates that were seen in the signal, but they were not strong enough. So we think that based on exoplanet demographics and the dynamical analysis, these planet candidates are more likely, I would say, to be real planets because they are where we predict them to be. Interestingly, also between planets E and F, we predicted there's one more peak, and that falls squarely in the habitable zone. Because the other planets are more massive than the Earth, it is likely that if there's another planet there and it follows the same size distribution, it would be more massive than the Earth. So it could be either a massive super-Earth or a low mass sub-Neptune. So that needs to be seen. Nevertheless, this is a very specific prediction where we can and have predicted the radial velocity amplitudes, the periods, and they can be verified by follow-up radial velocity observations and potentially with direct imaging too. In the latest study, we have pushed Dynamite even further, and this presents a detailed study of the dynamical stability assessment methods. I will not go into details here, but we basically compared these 3 different approaches, and we found that the results were all very, very similar. But in cases where there are resonances are important, there is an advantage to doing bigger n-body simulations, etc. And this we also applied to a specific planetary system. This is the closest planetary system with 6 known planets, HD 219134, and also 1 prime candidate for characterization. So I think this is really exciting. I will mention Ritwik Basant's paper that is using Dynamite framework, but he added this temperature assessment prediction module too, and we applied this to E Eridani, which is the 5th closest sun-like star with 3 RV planets and 3 RV candidates. And I will, for the sake of time, I will transition to other results too. But I wanted to just mention that I am very excited to see the predictive power that we have for systems once we have a few planets known in the system, both in the solar system and beyond. And there's a growing number of papers using this framework. It is publicly available, so if you are interested, you can find this on GitHub. And some other teams, one led by Kevin Hardegger-Ullman, have utilized this for their own studies. Now, I want to basically transition in the remainder of the talk and then explore a little bit how this general framework that I showed you, basically demographics information, complementing, supplementing specific but incomplete and uncertain information on a given system, how can it be used also on a mission level, population level ways to enhance mission efficiency. So this goes back to one of the projects we led with Alex Wixell. In 2020, we published this study. The question that we set out to explore was basically a long-standing problem with direct imaging. When you take a direct image of a planetary system, on just in one planet, in this case, in the simplest case, in the center, you basically see a dot that is separated from a central star, which is a coordinate. And you have to figure out how large is the planet, what is the orbit, orbital eccentricity, semi-major axis. Is it going to fall in the habitable zone, or even is it even a planet? And of course, in a real image, you would not have 1 dot, but you would probably have maybe 12, 14 different dots. Some of them would be background objects, some of them would be bigger planets farther out, some of them could be smaller planets. So you can see here just a couple of examples. There's an infinite number of orbits that are consistent with one dot. And so how would you find out whether this is really an exo-Earth candidate in the lower right, or false positives, one of the many false positives. So these can be just also Earth-sized planets that are projected into the habitable zone, or it could be larger planets with a lower albedo or seen at at a phase angle that makes them appear less bright. So this is a problem that is recognized to be a problem. A study by Guillemond and Nikon argues that 77% of the candidates that will be identified are actually not Earth. And so what Alex and I did, we showed that if you actually fold in demographics information, then you can significantly enhance the mission's ability to recognize, to identify correctly which are the false positives and which are the most likely exo-Earth candidates. And so Alex has done a really detailed analysis of what are the contributions from subterrestrial, terrestrial, and ice giant planets using Kepler-based demographics, and what are the key contributors as a function of different type of information. So we also consider that, for example, you have an initial detection, but you had also radial velocity information that will exclude some of the massive planets, for example, from the false positives, but will leave planets that would not be detected as false positives there. What happens if you have a debris disk? So you have some handle on the inclination. What happens if you revisit and you have astrometry or color information, etc. So while I don't go through all the different cases we studied, we showed that if you fold in the demographics information, you can get a very significant increase, typically about 33% increase in the efficiency of your identification of your candidates, and then actually also in the total mission time that you spend on that. So with some nominal values, we were able to translate that to actual mission time. And so in fact, the simple approach of just revisiting everything with the right colors is better than revisiting everything, but it is not close to the optimal approach. So this is, I think, obviously this can further improve as the more demographics information, more constraint we have on systems, the more we can integrate that, but it already demonstrates a very significant improvement. Now, the last set of questions I wanted to mention here, last set of studies build on this even further, asking a question, what actually can we learn from a direct imaging mission? So to the very first level, of course, the goal is to identify potential exo-Earth candidates and then figure out whether there is life. But in reality, when we ask the question and we want to answer this question, whether or not there is life, we will need to understand the complex ecosystem and the complex evolutionary pathway for these planets and the diversity of planets. So I think one way that I think we should be starting to think about missions is not so much how many planets they can detect and what sort of signal to noise we can get for a given atmospheric species, but rather what hypotheses about the planets can we test. And so this is, in fact, I think hypothesis testing really essential to fundamental science. And I think we need to kind of use this sort of assessment when we compare different kinds of missions and sample definition. So the simplest, I think, hypothesis that you can potentially test, and this is what we set out when we put forward this idea, is can we test whether or not most Earth-like planets evolve as Earth did in terms of their atmosphere. First, an oxygen-free atmosphere and then transition to an oxygen-rich atmosphere. What happens if all of them evolve at the same rate? What happens if only a fraction of them evolves at this way? Or what happens if the oxygenation timescale is actually varies from planet to planet? So we published a paper in 2020 with Alex exploring this and basically doing a Monte Carlo simulation, assigning oxygenation timescales to planets that are identified as exo-Earth candidates, and then also varying the fraction of planets that has life on it, so whether they will ever oxygenate or not, and even considering the possibility that some of them may have abiotic oxygen in them. And so we asked the question, if with this population we actually want to figure out test hypothesis, how large a sample we would need for the different possibilities. And I will just highlight here that it is basically depending on the occurrence rate of life and on whether or not many of the planets, of course, follow Earth-like evolution. Depending on these factors, you can identify, which we did in the figure, what is the size of the candidate sample size that you need to study to test hypothesis. So I think that's a very nice example for how important the hypothesis testing is. We also pointed out that because of ultimately this hypothesis relies on comparing planets of different ages somehow to see differences. So actually having samples in which there is an age range, young planets, youngish planets included, that increases the diagnostic power. So that is, I think, an important point too. Finally, we basically took this to the next level in a framework we developed with Alex, which we call Bioverse. So Bioverse is a general framework that allows you to take your favorite mission concept or a mission concept you want to do a trait study on and ask the question, what is going to be not just the number of planets I can detect, what sort of hypothesis can my mission test? And so this is a modular framework where you can make decisions if you don't like our assumptions, or not that there's anything wrong with your assumptions, but if there's new demographics information, you can update some of these models. In those cases, you basically can change those models and execute the program. What Bioverse does is basically it creates mock, in a sense, mock universes, if you like, or mock planetary systems, creates stars from a nearby, based on nearby planetary system sample or a mass function, creates planetary systems that are drawn from the exoplanet Kepler demographics, and then it can classify planets. You can assign types of planetary atmospheres to your planets based on planetary evolution models or types of atmospheres. We followed, for example, the solar system as example, and then apply population level trends. That creates planet population that you can then simulate a synthetic survey of. You have a survey description, which includes the mission capabilities, the mission strategy, follow-up strategy, etc. So it determines basically how you prioritize and observe your targets, how much information you can gain from the observations. And so you will have simulated synthetic results from your survey, and then you can ask the question, given my hypothesis, can I actually get an answer, a statistically significant answer to this hypothesis? Can we reject the null hypothesis? What sort of complexity my hypothesis can have to be scientifically testable? So I'm very excited about this. I think this is a very important tool. We have tested and demonstrated its use on 2 example science cases, Earth-sized planets in the habitable zone, and whether or not Earth's habitable zones really exist. Could we detect them as an enhanced likelihood of Earth-sized planets having water vapor in their atmospheres? And the other one we tested again with this framework, whether if you have Earth-sized planets in the habitable zone, and the hypothesis is that they show also an age-oxygen correlation, can we test that? This Bioverse has both a transit imaging, spectroscopy, and direct imaging modes. And Bioverse produces this nice set of figures where you can basically assess the diagnostic power of your mission, simulate outputs, and then figure out for what is the probability, the likelihood that you actually can test your hypothesis as a function of, for example, Earth's occurrence, life's occurrence rate, etc. I will, because I'm running out of time, I will not go through these figures, but I showed you basically examples for both direct imaging, diagnostic power analysis, and also transit diagnostic power analysis. And I think these are really nice examples of how we can integrate basically demographics level information to do a better assessment of a mission's diagnostic power than what we could do with just assuming that the more planets we can see, the better it is. And so what are next steps for Bioverse? We are working to update stellar and planetary system catalog, in part based on the latest Gaia data. This is where Kevin Hardigy-Ullman is leading. We are working with Regis Ferrier and Stefan Manzave and Antonin Affolter to integrate an entire ecosystem model they published to provide basically a simple but fundamental, simple ecosystem model and evolution pathway that we can allow us to test hypotheses. We plan to apply this to the US ELTs to assess their hypothesis testing power. and importantly, test these different architectures for a 5 to 7 meter diameter system. So with that, I'm coming to the end. I basically, the key point really here is that Alien Earth is providing a framework where we can integrate many different types of information from planet formation, exoplanet demographics that's emerging, better understand these processes, but then also take them and create through the frameworks I described, Dynamite and Bioverse, into tools that allow us to better define our missions, better understand what type of information we will be able to get out, and inform our target selection and guide follow-up observations. I will stop there and thank you all for your attention.
Thank you very much, Daniel. It's a very interesting talk. So if you have questions, please raise your hand. And we have questions from Steve.
Yes, thanks, Dániel. That's a great talk and a great project. You can probably use the code you described to predict what I'm gonna ask. You've touched briefly on debris disks and things, but what about dust and by extension, minor bodies in the system? For example, in the solar system, if I remember right, there was a planet predicted between Mars and Jupiter. If you add the asteroid belt there, could you say this is probably not a planet there? Or EPS-ARI, for example, you have hardly any constraints from your code on EPS-ARI because there are no known planets except the one Jupiter-Mars-ish planet at something like 4 AU. But if we could predict where the habitable zone dust in this system is, for example, from our LPTI observations, could you further constrain where planets would be there?
That's an excellent question. Yes, and so basically that is entirely possible, and we have been looking into that. We didn't do it yet. The little bit the challenge will be there to understand better what is the relationship between minor bodies and planetesimal belt and the current state of planets. So that's obviously an active area of research, but we can add that. And what we have been also doing in a few cases where we can also test hypotheses with Dynamite, we can say if actually a minor body belt means that there is no planet, then we can basically see what would be the prediction for the locations of the other planets. And what if you don't make that assumption? And so sometimes that results in two different predictions. And so we can actually translate to different observables. So we can go back and then try to test our hypothesis. Yeah, and I'm glad to chat more about this. This is an interesting topic. Yeah.
Thanks.
And Ivy.
Yeah, great talk, Daniel, as always. I had a question about Alex's work on the Bayesian classification for EECs. I was wondering, you mentioned, of course, that you bring in kind of a photometric repeat observations. Did you start to bring in spectroscopy or think about sort of the most efficient way if you're going to follow a single photometric detection with a spectroscopic measurement combined with all the other factors that you mentioned? What would be sort of the most diagnostic in that sense?
So that's a very good point. So basically we looked at photometric information based on templates that we drew from the solar system primarily. And next steps in the modeling could be that if we have compositional abundance constraints, for example, from a retrieval, then we could use that to, and initially probably they are going to be uncertain and etc. But I think that is something that could be readily folded in, and I think that could be a very nice next steps that we haven't done it yet.
Yeah, I mean, it could be interesting because it would fold the other way as well, is retrievals would be more powerful if you could fold in all the information that you're gathering for all these other parameters. So that's why I thought it would be, synergistic.
Yes. Yeah, I think that's right. And I think, one question is also always the cost function. For like a photometric point, it may be much easier to get that than for for a spectroscopy. So I think that basically defining the cost function and then also the input library that we use, the spectral library, those will be important steps to integrate that. So, and I spoke with a couple of groups who were all interested in giving us spectra for spectral libraries that we can use for that. Yes, and I think that would be a nice step to take. Yeah, thank you, Avi.
Great.
We have one more question from Rhino.
Hi, Daniel. That was an excellent talk. My question is perhaps a bit speculative and very big picture, and it also pertains to Alex's work, the Bioverse. As you probably know, and perhaps everybody here knows, there's this thing called the Fermi paradox, namely that where are the aliens? If Earth-like planets are as common or as numerous, maybe not so common, but numerous enough, why haven't we seen them? That's a very short way of putting it. There are, of course, many details of that. And the thing that struck me is it's, the timeline of the great oxidation event for the Earth, that it's rather, it's late in the sense that it's several giga-years into the evolution of the planet. That part, at least that part of Alex's analysis, can that help shed light on or illuminate somehow the Fermi paradox? That the timeline, how long it takes for a planet to become strongly habitable, if I can use that term, habitable as in Earth-like as we know it, as opposed to very early Earths 4 giga-years ago. It was, I would imagine that we would still consider the Earth as we know what it was like 4 giga-years ago. We would still consider a planet like that habitable. So just the timeline of the great oxidation event, can that help illuminate the Fermi paradox?
So I think that's a very important point, that there is really important information in the time, oxygenation time. And I think David Kipping actually had a paper on the oxygen, what can you do with one data point and the relatively late oxygenation event in terms of reverse projecting statistics. But I think actually measuring the distribution of oxygenation, or at least constraining the typical oxygenation timeline and maybe a spread would be quite important. On one hand, if we actually find many young planets, 100 million or 200 million years with a lot of oxygen, that would be a good argument for not using oxygen, or for oxygen probably having a significant abiotic source too. If we may find that most of the planets didn't undergo this oxygenation, and I think one question, I like this suggestion. I think one practical question will be whether we have a large enough sample that even a null detection can basically help resolve the Fermi paradox in terms of basically putting an upper limit on the number of planets that could be, in a sense, visited by and then occupied by an alien civilization. So I think, that measurement, the oxygenation timeline and the frequency when it occurs, it's quite important. Yeah.
Okay, thank you. Of course, this is tied in with questions of metabolic pathways. Maybe there are other things other than oxygenation that might lead to high energy density metabolic pathways.
Yeah, so with I briefly mentioned in passing, with the work we are doing with Regis Ferrier and Antoine Affolter and Stefan Mazzavi, they have an ecosystem model, and they have methanogenesis, for example, methanogenic pathways and metabolic pathways model. And so we will want to see what, with the kind of model sample we will get, what sort of metabolic pathway transitions could be testable. So I agree. Yeah.
Okay, great. I think we are out of time, and that's all. Thank Daniel again for this very interesting talk.
Thank you all very much. Thank you.